Okay, thank you very much. Thank you very much to the organizers for the opportunity to speak at this workshop. And okay, let's start right ahead. So by now, I think that we all agree on what the isoperimetric problem is. So let's take this slide just to fix some notation, right? So the isoperimetric problem tries to answer the following question: what is the minimal perimeter needed to enclose some volume in some given ambient space, M? So the ambient space can be anything as long as it makes sense to speak about volumes and perimeter. But of course, in this talk, we are going to focus in the case of the Riemannian manifold. So if you want to approach this type of problem, you usually try to answer the following 4 questions, right? So the first one is about analysis of the isoperimetric profile. So the isoperimetric profile, I, is a function taking some volume V and giving you back the minimal perimeter among all sets belonging to some class in which it makes sense to speak about perimeter. So in Rn, for example, in manifold in general, are sets with finite perimeter, Cauchy-Pelli sets, with the constraint on the volume. So of course, you can do analysis on this function. You can and you can infer properties of it. Then the second point is the existence and regularity, okay, of isoperimetric regions. So in this talk, I will speak about isoperimetric regions, isoperimetric set, optimal sets, minimal sets. All of those are synonyms for sets that actually verify the minimal of the isoperimetric profile. Then, of course, what you would like to also to have and to determine is an explicit description of isoperimetric sets. So of course, this is a kind of very difficult problem in general. So usually, description can be also thought in a more qualitative sense. So, for example, is the set convex? Is it set connected? Is it regular? How regular it is? But of course, the Graal, at least in my opinion, of this general isoperimetric problem is to have kind of an explicit geometric description. So I tell you the ambient space, I tell you a volume, and you just give me the set in front, right? I can see it, I can measure it, makes sense. And then once you have this, you can, of course, ask yourself questions about strong stability, right? So you want to kind of quantify the isoperimetric gap with some function, some distance, some notion that tells you how far is the set E. I did the same probably. Maybe no, I didn't do. Okay, thank you. Okay, so yeah, you want to quantify the isoperimetric gap. Okay, so the first part of this talk will be about this point here, so description of isoperimetric sets in some ambient space, the complex hyperbolic space, and the second part of the talk will be about stability. Okay, so why explicit characterization of isoperimetric set is difficult? Well, this is a slide with all the manifolds, okay, without boundary, in which we have explicit geometric description of isoperimetric sets. Okay, you can argue that there are a lot, but if you compare this list with all the possible Riemannian manifolds, they're not a lot, right? And so I'm not going to through all of them, but essentially they're all kind of model spaces and product of model spaces, with some restriction on the dimension because of regularity issues. But a lot of ambient spaces are missing, right? So what about S2 times R2? In my opinion, is still open. On my knowledge, is still open. The complex hyperbolic plane, the complex projective plane. Also in the Lie group theory, the very basic Heisenberg group, not even the sub-Riemannian one, really the Heisenberg-Riemannian group, still unknown. Okay, we have comparators, but there is no proof yet of classification. And so the reason is the following, why it's so difficult, because there are essentially 2 ways of classifying isoperimetric sets. And those are the ways. So the first one is kind of the original one, and it's by symmetrization. So symmetrizations are all the procedures that takes a set, make some geometric manipulation with the set, and give you back another set, which is a better competitor. So it has to preserve the volume, and it has to decrease the perimeter. And of course, you want to gain in terms of symmetry, right? So you want your set to be preserved by some subgroup of the isometric group of your ambient space. I will go back to symmetrization with a fixture later on. And then the second way you can approach this problem is using calculus of variation. So if you have you have existence and some regularity for your isoperimetric sets, then of course, since they are globally minimizers, in particular the minimizers at the first and second order, and so computing the first and second variation of the perimeter, you can actually produce PDEs and do PDEs analysis. So in this particular sense, analyzing the first variation, you have that, so there is a quantity that is preserved on the boundary, the mean curvature, and this is related is related to the work of Alexandrov by the super famous approach of moving plane methods and reflection with respect to planes. And the second approach is computing the second variation. And so it tells you essentially that you have an operator that is positive definite, and choosing special perturbations, you can infer geometric properties of your stable object. And this is initiated by the work of Barbosa, Do Carmo, and Escher, but we are also going back to this later. But so kind of the moral of this slide is to tell you that if you want to classify as a perimetric set with the tools we have at the moment, you need to search for symmetries, right? So this, it stays even in the name, it's a metrization procedure. And of course, if you want to make this type of arguments work, you also need symmetries of the ambient space, but also of the isoperimetric set. And so if we want to look in ambient spaces in which we want to have some hope of classifying as a perimetric set, let's look into symmetric spaces. As in particular, the complex hyperbolic space. So everything I'm going to tell you today works in a much general class of manifolds. They are symmetric, but I mean, for clarity of exposition, I will stick to the complex hyperbolic space. So at this point, I could give you a model of it. I can give you the Beltrami-Klein model, I can give you the ball model, the projective model, but I don't think it's very informative, right? So let's just talk about kind of properties of this space. This will be enough for this talk. Okay, so if you don't like Riemannian geometry that much, it's a diffeomorphic to R2M, right? So you can see it as the Euclidean space with some weird metric on it. It is symmetric. In particular, the Riemann curvature tensor is parallel. This is going to be very useful later on. It is a Keller manifold. So in particular, it's a complex manifold, so there exists a complex endomorphism. So a map from the tangent bundle to tangent bundle such that squared gives you minus the identity. It is pinch, so the sectional curvature lies between two negative numbers depending on your favorite renormalization. For me, it's -4, -1. And it's very interesting because the way the sectional curvature is distributed is with respect to the underlying group structure, right? So if you fix some direction V inside your complex hyperbolic space, then you can compute J times V, right? So the complex multiplication of V. This will span a plane. And in this plane, the sectional curvature is -4. Then if you take all the orthogonal planes with respect to V and J of V, let's say W, then this plane here, we have curvature -1. So, okay, the sectional curvature is not constant, right? It's a complex space, but it's at least distributed with respect to some kind of, in a nice way, right? With respect to the group structure. Very useful also for later. And finally, this space is 2 points homogeneous, meaning that if you have 2 points here and 2 points here with the same distance one to another, there is a global isometry sending these points over these other points. So it's very symmetric in that sense. In particular, now imagine that you have like a geodesic sphere, right? So you fix the center, you take 2 points on the surface of the sphere. There is an isometry sending that point to the other point, right? By 2-point homogeneity. So in particular, geodesic spheres are, so the isometry group acts in a transitive way over spheres. So spheres, geodesic spheres in these spaces are homogeneous spaces. They have for free constant mean curvature. And by the discussion we did before about symmetry, those are kind of the most symmetric subset you can have, right? For the meta theorem of the fact that you want to search for symmetries, let's say that the spheres, geodesic spheres, or geodesic balls are the best candidate. And this motivates the Gromov-Soss conjecture, so that geodesic spheres are isoperimetric regions in the complex hyperbolic space. So I'm not going to tell you something I don't have. I haven't solved this conjecture. This remains the conjecture, but I will give you two results in this direction. Okay, good. So if we want to understand the problem, we have to understand the anatomy of our competitor, right? So the sphere. And so the thing goes as follows. So you have your geodesic sphere, right? You have the center of it. Take a direction V, take J times V, and take another W orthogonal both to V and J of V. Okay, then of course this triple, you can parallel transfer it till the surface of the sphere, right? And since I told you before that the Riemann curvature tensor is parallel, okay, this splitting will be preserved from the center till the surface of our sphere. So what does it mean? It means that, okay, this now is the normal. So let's fix once and for all an origin O, and then we write all the points in normal coordinates. Some r is the distance from the origin, and omega is the coordinate in the sphere, right? Okay, so here we have ddr, which is the normal. We have j ddr, which is called the characteristic direction. So in particular, it lives on the tangent plane of the sphere. And then we have all the orthogonal directions, right? And so we have that the tangent space, if this is point x, right, the tangent space of the sphere will split in a vertical direction and all the orthogonal ones, right? So v of x is simply the span of ddr. So it's this direction here. And then we have all the others, okay? Okay, maybe I don't want confusion. So in my talk, when I will speak about distributions for me are a smooth choice of subspaces of the tangent bundle. Okay, so geometric, that's a distribution. So in particular, this is a distribution. Over my sphere, and so we can complete it, right? So now, if we add this vector here, we have at each point of the manifold a splitting of the tangent space into a vertical component and then an horizontal component. So maybe let me write it here. So we have that Tx of m, okay, for x different from the origin. At the origin, this discussion doesn't make sense, of course. But this splits into a vertical component, so it's a one-dimensional vector space. So it's this j times d of dr plus an horizontal component, okay, which is this d, and then you add also the normal component. Okay, this dichotomy, so this splitting tells us two things. The first one is that spheres are fibrated. So those spheres have constant mean curvature, constant principal curvatures, but they're not all the same. So there is kind of a curvature which is exceptional here. That's why they're complicated objects. They're not umbilical. So all the machinery working with umbilical sets do not work here. And then the second thing that one has to see is that this splitting essentially is telling you that fixing one point, taking normal coordinates and doing this splitting, you will have some direction. And if you look in those directions, it happened again. I don't think I know the password. So like, I finished speaking about this. So in this direction, if you look in your manifold in that direction, you will see a hyperbolic space of curvature -1. If you look in this other direction, you're looking at a hyperbolic space of curvature -4. Okay? So this tells us a very important thing, so a very important comparison result. Because if now I call superscript v and superscript h the orthogonal projection of the vector in the vertical and horizontal component, I can express the complex hyperbolic metric in terms of the real hyperbolic metric in the horizontal component, and then you have this factor correcting the curvature and the vertical component, where I'm identifying the complex hyperbolic space with the real hyperbolic space in normal coordinates. So you take the normal coordinates on one side, the normal coordinates on the other side, up to the choice of directions. You can identify them, right? Both of them are diffeomorphic to Rn. And so you have this very nice comparison result. And so essentially, you started with a problem that was in the complex hyperbolic space. You end up in a problem which is in kind of in the real hyperbolic space with some anisotropy, or with maybe some abuse of kind of terminology, sort of sub-Riemannian. Okay, good. Why this comparison result is very useful? It's because now we can express perimeter and volume in the complex hyperbolic space in terms of this. Okay, so the volume is nothing in particular, right? So it's really like the volume and exponential coordinates. The exponential map is always a radial isometry. You gain this density factor here. And now the perimeter in the complex hyperbolic space can be computed in the real hyperbolic space with the same volume. So volume correction is some sort of kind of an artifact coming from the exponential map, and then a term that is kind of anisotropic. Very nice. We don't like this term. we kill it. So we say that E is Hopf symmetric if the normal at E, it's always horizontal. So the vertical component is always equal to 0. In particular, if that's the case, that's nice, right? Because now we have that the perimeter of E, if it's symmetric, it is exactly the perimeter and the volume in the real hyperbolic space with the same density. So we transform a problem in the complex hyperbolic space with complex direction, anisotropy, etc., into a problem that is a weighted problem in the real hyperbolic space, a space which can kind of control much better. Okay, very quickly, examples of Hopf symmetric spaces, geodesic spheres centered at the origin, right? We hope that our competitor is still a Hopf symmetric set. Or in particular, I will not go into details, but this kind of justifies the name Hopf, are star-shaped set such that the profile function is constant along Hopf fibers. That's why. So if you want, those are sets that can be parameterized over a complex projective space. There are a lot of them. That's just kind of the motivation. Right. And so if we are able to prove this term here, so for any radially strictly log convex density F, centered geodesic balls are uniquely isoperimetric in the real hyperbolic space with respect to the weighted perimeter and weighted volume. Then, taking F equal to the hyperbolic cosine, we prove that in the complex hyperbolic space, balls are uniquely isoperimetric in the class of Hopf symmetric sets. Right? And also, you can get some kind of suboptimal result for general set E. If you then go back and look at the anisotropic kind of representation of the perimeter inside the real hyperbolic space, you can actually control the perimeter in the complex hyperbolic space of set E with the perimeter of the geodesic ball with the same volume in the complex hyperbolic space, and then you gain this error here where R of E is the circumradius. Okay, so it's a ball containing your competitor, and of course the bigger the ball, the huge the error is, but the smaller it is, the hyperbolic sign goes to 0 also. This tells you, okay, the smaller is your set, the more similar is the complex hyperbolic space to the real hyperbolic space, which is something that you are expecting. Okay, but the important result is this one. This is kind of like a very stupid consequence, just looking at the formulas. Okay, so why log convex? So I will not lose time here that much, but of course this problem of kind of classifying isoperimetric sets with radial weights was of course introduced first in the Euclidean setting, and essentially in this paper, Rosales, Cagnette, Boyle, and Morgan, they did many things, not only this of course, but like they also noticed that if you have a radial weight in the Euclidean space, spheres are infinitesimally stable if and only if that weight is log convex. Okay, and this is also true in the real hyperbolic space, by the way. And so Bracchi conjecture out of this observation that not only this is not only those are stable, but they are global minimizers if the weight is log convex. Then a bunch of people proved the kind of intermediate results with very nice technique, where the large volume regime, small volume regime, existence boundedness also in the more general setting. But the full proof was given by Chambers in 2019, proving through Bracchi conjecture. And so what we did essentially was to kind of generalize or kind of extend the strategy of Chambers in the real hyperbolic space. So the proof of Chambers is one of my favorite proofs. It's one of my favorite proofs, and I will give you an idea of why it's so nice, and I'll give you an idea of the strategy. Let me. So what you do, you fix a volume, okay, and you take your isoperimetric set. You know that it exists by classical arguments by Morgan, because in particular you can trap volume escaping at infinity, so you can perform a compactness argument, right? Okay, good. And then, okay, you have your set here. Let's say that it looks like this. You have no idea how it looks, right? We are in the real hyperbolic space of some dimension. And now you perform a spherical symmetrization. What does it mean? It means that you take centered spheres. The center here is a bit off. Let's put it here. Okay. And you intersect the spheres with your set E. Okay. Colors. And then you look at the intersection of those spheres with your set. Etc. And then you replace those intersections with the spherical caps with the same area, centered to an axis, right? So here you have this, you have this. Right. So let me give you some, I don't know, something that looks a bit spherically symmetric. Okay. Yeah. Okay. And this is E star. The weights are radial, right? So by Fubini, E star will have the same volume as E. Everything is radial. And then you can check that the perimeter of E is less or equal to the perimeter of E star is less or equal to the perimeter of E, essentially by Kohara formula. Very nice. And so we started with a problem in the complex hyperbolic space. We reduced it to a weighted problem in the real hyperbolic space. We use a spherical symmetrization. We end up in a problem in the real hyperbolic plane. Because now this set here can be described, and now we are in real hyperbolic plane by a curve. Maybe there are more connected components, but okay, just take the connected component further away from the origin, and you have some gamma. You can also infer regularity properties of this gamma, right? Because you know that we know that the set E and also the set E star will have some regularity, very deep results that we all know by now, right? And so we also have a regularity of gamma. In particular, you have the E is itself isoperimetric, so is minimizing at the first order. And so the mean curvature of E star, or E because we replaced E with E star, will kind of so gamma will inherit at ODE coming from the constancy of the mean curvature of the starting set, of this spherical symmetrized set. And now what you have to do, so this is ODE, it's not really important what it is, but like it's an ODE in terms of gamma. And now you do a very subtle ODE analysis of gamma. And so you prove the following. So either gamma is a centered circle, and you're happy, there's nothing to do, or gamma has to do something weird. And the weird thing gamma does, I did here a picture in the real hyperbolic space. I think there is a problem. I just click here. With some list. Okay. Gamma goes up, then it curves down faster, and then it goes up again. And this cannot be a profile of a spherical symmetric set. Done. Okay? Super nice proof by Chambers. So what we did is a kind of extend this proof in the real hyperbolic setting. The main difficulty was, of course, doing this comparison results. So you have to kind of fix a good frame of reference. And okay, in the hyperbolic space, this frame of reference has kind of curvature, so there are a lot of terms going out. But the strategy is the one of Chambers. This is the first part of the talk. And then, how much time do I have yet? 15 minutes. Okay, I will probably finish earlier. It's good because I have coffee break. So let's go. Okay, let's talk about stability now. Okay, what we know about stability of spheres in the complex hyperbolic space. So what we know is that spheres are infinitesimally stable. So by the paper I cited before, Barbosa, Doccarmo, and Eschenburg, we have that, I will not touch this anymore, we have that the sphere, so if the second term of the Jacobi operator is constant, then your set is stable if this constant is equal to the first eigenvalue of the Laplacian over the surface. And so this is the case for spheres in the complex hyperbolic space, and so everything boils down to computing the first eigenvalue in the complex hyperbolic over the spheres. In technical terminology, those are Berger spheres, so fibrated spheres. And then, so that's what they did. And also, let me mention that recently the full spectrum was computed with using kind of abstract tools of algebraic tools of Lie group theory by Bettiol, Loret, and Vittore. And then also the quantitative C1 stability, the one like the Fuglet, the one we've seen before in the previous talks, was also a consequence by an implicit argument in the PhD thesis of Gilles Caron in 1995, where he introduced this notion of being geometrically stable. So what we proved is a kind of a constructive proof of this C1 stability, sort of explicit proof of C1 stability, using again the fact that you can compare the complex hyperbolic space to an isel space, paying the price of having anisotropies and weights. Right? And so essentially that's the theorem, right? So you are in the complex hyperbolic space, you fix a big radius R0, and then you have kind of a uniform epsilon, so that for every R less than R0, and all perturbation of the sphere with some profile function rho, with the rho that has the small enough C1 norm, then you can control the isoperimetric gap by some constant R squared and the W12 or H1 norm of the perturbation. And then, so this proof is constructive in the sense that if you're brave enough, you can go through it's a huge Taylor expansion essentially, so you can actually quantify all the constants. And then you can compute epsilon. What I can say to you is that in this particular proof, epsilon goes to some constant, of course, positive constant as R0 goes to 0, right? Because everything is uniform. And it behaves some kind of negative exponential as R0 goes to plus infinity. Please. E is general, yes, definitely. Just one perturbation. Yeah, exactly, because now the same game we did before by comparing the real hyperbolic space with the complex hyperbolic space with the real hyperbolic space, you can do exactly the same comparing the real hyperbolic space to the Euclidean space, just by lifting on the tangent plane. And so you will have a similar splitting. Now you have to be careful, you also have to split in the normal directions. But essentially, you see, you can still write the metric in the complex hyperbolic space as the metric in the Euclidean space with some correction weight with respect to the projection of the normal over these distributions. And in particular, you can now write the perimeter of E. In this particular case, E is what is called a nearly spherical set, so it can be written as a graph over the sphere with some expression, okay, some projection of the gradient of rho with respect to the vertical and the horizontal component. And then, okay, then you can do an analysis on this. Okay. I mean, it's not a nice formula, but it's a formula that you can work with. Huh? It's impossible. I don't know. Telecinesi. Okay. Right. So essentially, you do like a huge Taylor expansion of this guy here, and at some point, you hope to see the first eigenvalue of the Laplacian popping out, which is the case. So you can actually control the kind of the spectral gap and taking care of all the lower order terms. And a nice consequence of this theorem, because the kind of the bound is uniform in R0, is that you can prove the conjecture for small volumes. So let me say again that this was a known result with implicit arguments in the PhD thesis of Nardulli, following an idea of Kleiner. But essentially, we gave a kind of an alternative proof of it, which is sort of constructive, again, theoretically constructive. And essentially, you use the fact that, okay, your complex hyperbolic space is a space that has bounded geometry, so the Ricci tensor is bounded from below by a negative constant, but is bounded. And so you can use the fact that for a small enough volume of the isoperimetric set, you have the decay of the emitter, and also you have kind of an approximate isoperimetric, kind of Euclidean isoperimetric inequality with some huge constant if you kind of confine E inside a big ball with a big radius R. And then this allows us to localize the argument. Then we take the kind of the perimeter as it was expressed using kind of the biprojection of the vertical and horizontal distributions. You quantify everything. You do and you can actually show that the lifted set will solve essentially the isoperimetric inequality in the Euclidean space with some error that is kind of proportional to its volume. And here we apply very deep results of stability, strong stability of isoperimetric set in the Euclidean space by Fusco, Maggi, and Pretelli, Ciclesi, Leonardi, Ficalli, Maggi. And then that was already discussed before today. And what you gain is an L1 closeness. Well, L1 closeness of your competitor to the ball, the centered ball in the lifted tangent plane. Now you take a sequence of kind of sets with volume going to 0. You have to choose carefully the point where you lift them up to the tangent plane. You rescale them so that they all have a volume equal to, I don't know, the unit ball volume equal to 1. Doesn't matter that much, but essentially afterward, so this will give you L1 closeness. You prove that there are almost minimizers. You apply regularity theory for almost minimizers. You gain L infinity closeness, and eventually you gain regularity, and then your stability result for kind of C1 perturbation kicks in, and you prove that those are actually spheres for small enough volume. Yes, that was all. Thank you.